All right, so we're talking about segment addition and midpoints in Unit 1, Lesson 2. The goal is for us to find the distance and midpoints of line segments. So if we take a look at these four scenarios, the question is how would we evaluate the length of each line in how would we evaluate the length of each line segment below? So here we have a line segment. How could we find the length of that line segment? Another question would be, over here we have a little number line and we want to know the length of DE. So, no, that says B, sorry. We want to know the length of DB. So how would we find that length? Okay, then we have another line segment, but we have some information that we have to work with. We know that the whole line segment has a value of 7x plus 6, and we know that FG, the segment from F to G, is 4x. We know the segment from G to H is 24. And then finally, we have a line segment within an XY coordinate plane. And so we're going to talk about in this lesson, how do you find the lengths of line segments? How can you find the distance between 2 points? Which the distance between 2 points is actually finding the length of a line segment. And so those are the things that we're going to kind of talk about in this lesson. So I want to begin by talking about this ruler postulate. It says the points of a line can be put into one-to-one correspondence with the real numbers so that the distance between any 2 points is the absolute value of the difference of the corresponding numbers. Okay, so let's just use this ruler for example. Let's say that we have the portion of the ruler where this is labeled 1, this is labeled 2, and this is labeled 3. So the points on this particular ruler, if we were to say that the distance between 1 and 3 from here to here, we could count and say that it's 2. Okay, we could look at it as take the 3 and subtract the 1, and we see that the length here is 2. And by the way, these would be inches. These are not drawn to scale by any means though. But also, we could say the difference is 1 minus 3. Well, the 1 minus 3 gives us a negative 2. Well, in this postulate, it says that the distance between any 2 points is the absolute value of the difference of the corresponding numbers. So if we think about the absolute value of 3 minus 1, you get the absolute value of 2, and the absolute value of that is 2. Well, if we do the same thing for 1 minus 3, the absolute value of 1 minus 3 is the absolute value of negative 2, and the absolute value of negative 2 is also 2. So the key here is that absolute value is important because distance can never be negative. So distance is always positive. And that is something that that you need to remember. Okay, so now we're going to talk about some other things. So let's talk about the segment addition postulate. Here we have a big segment, AC. The segment addition postulate says that segment AB, this portion, plus the segment BC, so from A to B and B to C, when you add those two pieces together, you get the whole piece. So segment AB, this piece, plus segment BC, when you add those two together, you get this big segment of AC. So let's look at that for example. So we have in example A, we've got a segment going from C to A. We know that this segment is unknown. We do not know what that measure is. We're not told what that measure is. We are told that this length from B to A is 3. And the other piece of the other piece of information that we know is that the entire segment C to A is 9. So if I wanted to create some sort of equation, we'll call this segment CB. If we take the segment CB and we add 3, we know that all of that together should equal 9. So what is the segment length of segment CB? Well, if we subtract 3 from both sides, we get CB equals 6. So the length of CB equals 6. And for the most part, we could have just looked at that and said, oh, we know that this length right here has to be 6 in order to add it to 3 to get 9. Okay, but this is utilizing the segment addition postulate. Now let's look at another example. Very similar. We know that this entire segment D to B is 7. And we know that this segment DC plus the segment CB equals the entire segment DB. So what do we know about DC? We know that DC has a length of 5x, plus we know that CB has a length of x plus 1, and we know that that equals the entire length of DB, which we're told is 7. So even though this information involves variables, we still have a way to find the length with the given information. We just created an algebraic equation. So in geometry, we will actually utilize some of the algebra that you learned in Algebra 1. So this is an algebraic equation. That's what the segment addition postulate allows us to do. So then let's go ahead and finish this. On the left side of this equation, I have a 5x and a 1x, so that's going to give me 6x. And I know that I have this plus 1, and that equals 7. If I solve this for x, I will subtract 1, so minus 1 minus 1, and that leaves me with a 6x equals 6. And then when you divide both sides by 6, we get x equals 1. So with this, I know by solving for x, I know that x equals 1. So I can determine that the length of DC equals 5 times 1, which equals 5. And we know that CB is x plus 1. And that would be 1 plus 1, which equals 2. And if you look at that, 5 plus 2 equals 7. So we just used a little bit of algebra to help find the lengths of all of these little segments. Okay, so now let's talk about another example, example C. Now, we are told that we are given segment AB is equal to x plus 7. We know that segment BC is equal to 2x minus 2, and the length of AC is equal to x plus 13. And we want to find the length of BC. Okay, well, let's take a look at what we have. We have a segment AB, we have a segment BC, and our big segment would be from A to B to C, so AC is our big segment. So if I wanted to draw this out, I could have A here, I can put B here, and I'm just marking. What do I know about A? I know AB rather is x plus 7. I know that BC is 2x minus 2. And I know that the whole thing, A to C, equals x plus 13. So if I want to ultimately find this length right here, I can set up an equation. I can take my AB, which is x plus 7, and add BC, which is 2x minus 2, and I can set it equal to the segment AC, which I know to be x plus 13. If I solve this for x, if I solve this algebraic equation for x, I can then go back and determine what the length of BC actually is. So cleaning up my equation, I have 1x plus 2x, which is 3x. I have 7 plus negative 2, which is plus 5, and that equals x plus 13. I will take this over there. So I have 3x plus 5 and equals x plus 13. I need to get my x's on the same side, so I will subtract x from both sides, and that's going to give me 2x plus 5 equals 13. And to solve for x, I will subtract 5. And I have 2x equals, my 5's will cancel, 13 minus 5 is 8. Divide both sides by 2, and x equals 4. So, x equals 4 is not what we're looking for. What we want, this question is asking us to find, is the length of BC. Well, BC is equal to 2x minus 2. If I substitute 4 for x, I get 2 times 4 minus 2, and this equals 6. So the length of BC equals 6. So if I needed the lengths of each segment plus the whole total, I have everything I need because I found x to be 4. So, just for the sake of doing so, this BC we found to be 6. AB would be 11, and my segment is definitely not drawn to scale. And if x is 4, 4 plus 13 is 17. And if we look, AB is 11 and BC is 6. Does 11 plus 6 equal 17? And it does. Okay? Okay, so now let's take a look at finding length on a number line. So I want us to find the length of FG. Well, F is here and G is here. Now remember, when you're talking about a number line, you have to use the absolute value. And I just like to start with the coordinate of the point that's first. So the absolute value, what is F? F is at 3, and I will subtract the x, or the point at G, which is 8. So 3 minus 8 is 5, so I'm looking at the absolute value of 5, and that turns out to be 5 because absolute value is always positive. So if we look at the point from F to G, this is easy to count. 1, 2, 3, 4, 5. So it makes sense. Okay, then what about from C to F? So here is C. So my C value is negative 4, and I will subtract, because it's the difference of F, which is 3. When you subtract these, you get the absolute value of negative 7. The absolute value of negative 7 is 7. If you count from C to F, from here to F, 1, 2, 3, 4, 5, 6, and 7. So you get 7. How about A to F? The absolute value, the point at A is -9, and I will subtract the point at F, which is 3, which is the absolute value of -12, and that is 12. So from A to F is 12 units. Well, how about from A to G? I want to find the length of AG. So the absolute value, the A coordinate is -9, and I will subtract G, which is 8. And that will give me the absolute value of -17, and the absolute value of -17 is 17. So if you count on the number line from A to G, you'll get 17. So distance on a number line always has to be positive. And by the way we were subtracting, we kept getting negative values, so we applied the absolute value to them to force and make them positive. Okay? Okay, so now let's move on to evaluating segment length on the coordinate plane. So we have 2 points, and there's 2 approaches that we could take to finding the length of a segment on the coordinate plane. Now the first thing I'm going to do is I'm going to draw a segment between these 2 points, and I kind of went past my mark there, but there's my 2 points, and I basically want that length right there. So couple of approaches. We can use the Pythagorean theorem, and the Pythagorean theorem actually applies to right triangles. But in a right triangle, we don't have a right triangle. But what if I did this? What if we created a right triangle by dropping a leg from this point down to this point, and then draw another leg over to that end point? So when we just dropped this leg down and then drew a leg over, we just created a right angle. And so this right angle is part of this triangle, and this now is a right triangle. So one leg we will label A, one leg we will label B, and this leg is now C. Now in terms of a right triangle, C equals the hypotenuse of a right triangle. And A represents a leg, and B represents another leg. So there is a relationship between the legs, A and B, of a right triangle with its hypotenuse, which we will call C. All right, so that relationship is, you can take this leg, which we're calling A, and squaring it. We will add it to the other leg, which we've called B, and squaring that. And that will, the sum of those two will equal the hypotenuse squared. So here's a nice little formula that helps us to find the length of this segment, or the length of that hypotenuse. All right, so let's do so. So could we count from here to here? Can we count, to find the value of A, can we count from here to here? Sure. 1, 2, 3, 4. So A is 4, so I'm going to have 4 squared plus. Now what's the length of B? And we can count here. 1, 2, 3, 4, 5, 6, 7, 8. So B is 8, and I will square it, and then that will equal this side right here, which is the hypotenuse. which is what we are trying to determine. The hypotenuse is always the side opposite the right angle. So now when I clean this up, 4 squared is 16. 8 squared is 64. And that will equal c squared. When we add these two together, 16 plus 64, we get 80 equals c squared. Well, the length of the hypotenuse is not c squared. The length of the hypotenuse is c. So for us to figure out what c is, I need to undo the square by taking the square root of both sides. So this is going to give me c equals the square root of 80. Now I can reduce that radical, or I can give my answer in terms of a decimal. And I guess I'll do both. So hopefully in Algebra 1, or even pre-algebra, you learned how to simplify radicals. So here's how I do this. The number 80 is not a perfect square. So what I'm going to do is I'm going to try to find factors of 80 that are perfect squares. And I'm pretty sure that 16 is a factor of 80. So I can actually look at this as the square root of 16 times the square root of 5. And I just always put the radical with the perfect square first. So now the square root of 16, what makes 16 a perfect square? That is 4. So I'll mark that out, bring out the 4. And 5 is not a perfect square, so the value of c is equal to 4 on the square root of 5. Now if I were to put that in my calculator, let's see what that would be as a decimal. And I'm going to pull in my calculator that I use. And so all I have to do is type in I need to clear that off. I'll type in 4. And I have a radical right here, so second radical. And I'll put 5 in it and enter. And so 4 on the square root of 5, is approximately 8.944. And I always round things to 3 decimal places. Okay, so 3 decimal places there. So I want us to talk about the distance formula. And I want to talk about how the distance formula is actually related to the Pythagorean theorem. So remember with the Pythagorean theorem, we counted from here to here to be 4 units. I think was A4, 1, 2, 3, 4. We said that A was 4, and we said B was 8. Well, let's look at this from a different perspective. So if A is simply from here to here, let's think about what's changing. When you go from here to here, you're changing the vertical value. So what is changing? Your y values. So your y values are changing. And when you go from here to here, your x values are changing. So how could I, let's think about this. For this leg, I could take the y value of 6, the y's, I would take the y values, which are 6, and I could subtract the y value of whatever that point is. And the y value of this point is 2. Now for my x's, from here to here, I have an x value of -5, and if I subtract the x value of this point, which is 3, then look at what I get. This I get as +4, and here I get -8. So if I were to look at the distance formula, and if I were to take the distance formula and I were to treat these as 2 ordered pairs. Actually, let me pause for just a minute. So I think I want to go this route. Let's talk about the a squared plus b squared equals c squared. So when we found a, we said that our y values were changing. And how did I do that? I subtracted y's. I went y minus y. And since a is squared, I have to square that. And then for b, I did -5 minus 3. So I subtracted my x's. And since b has to be squared, that would be squared. And then for c squared, that would equal c squared. What did we ultimately do over here when we got c squared? We actually took the square root of both sides, and we ended up with c equals the square root of, and in this case, I have y minus y squared plus x minus x squared. And this, the y's, could be replaced with a, so I would have a squared. The x minus x could be replaced with b, and that would be b squared. But look at this formula and look at this formula. And how are they related? Well, when we're talking about a right triangle, we can find the length of the hypotenuse using the Pythagorean theorem. But if we want to look at this simply as without the right triangle, we can actually find the length of this by finding the distance between those 2 points. And so to do that, the little subscripts here, they only distinguish between one x from the other. So the distance formula can be found by taking an x value, which we say -5, minus the x value of the other coordinate, square that, plus the y value of that first coordinate, 6, minus the y value of the second coordinate, 2. We have to square that, and then ultimately, that's all under the radical. So when we clean this up, the distance between the 2 points can be found by taking the square root of our -8 squared plus 4 squared, and we get d equals that -8 squared is 64 plus the 4 squared is 16, and when we add, we get d equals the square root of 80. And hopefully at this point you'll see that we found the distance between the 2 points, and we found the hypotenuse to both be the square root of 80. And then therefore we can simplify the same way we did before. Okay, so I'll kind of reinforce that a little later, but let's look at some examples. I'm going to try to close close this out by looking at a couple of examples. Example H says to find the length of the segment connecting these 2 points using the Pythagorean theorem. Okay, so I'm going to actually sketch this out. Negative 5, 6 would be over to the left 5 and up 6. Negative 5, 6. And then I have a point at 3, 2. So over 3, up 2. So that's 0.32. If I draw the length of the segment between those two, and I want to use the Pythagorean theorem, I'm going to have to create a triangle. So I'm going to come over and I'm going to go up. So my equation is a squared plus b squared equals c squared, where a is one leg and b is the other, but c is always the hypotenuse. So here's my right triangle. And if I go from here, which has an x value of 3, to here, then from 3 to negative 5 is 8. So this length is 8. So I have 8 squared plus. Now when I go from here up, I'm going from a y value of 2, to the y value of 6, and that's 4. And so this is going to be 4 squared, and that equals c squared. So really what I'm finding out, and as I looked at this, I really did not have any intention of finding the same information on the previous page. So we've already done this. What we find is that c is equal to the square root of 80, and when we found the distance between those points, we found the same thing. The distance is the square root of 80. So I didn't catch that until I started working those, that these were the same examples, or these were the examples that went with the previous graph. So let's talk about midpoint. I want to talk about midpoint so that maybe we can get through with this video. In geometry, the midpoint is the middle of a line segment. The midpoint is equidistant from both endpoints. The midpoint bisects the segment. So when something is bisected, it is separated into 2 equal parts. Notice the little symbol here. These 2 little symbols right here indicate that these 2 segments are equivalent. Okay, so an algebraic property of midpoints using the illustration above us. Algebraically, we would know that AM, segment AM, has the same value as segment MB. The geometric property of midpoints can actually be found when you have an example in the XY coordinate plane, 2 points. Then you can actually find the coordinate of the point by taking your 2 x values, adding them and dividing by 2, and then taking your y values, adding those and dividing by 2. Okay, so let me see something here. Okay, so let's just take a look at a couple of examples. M is the midpoint of segment AB. Okay, so we've got a segment AB. Here's A, here's B. The midpoint, we're told, is M. If AM is 5x plus 9 and MB is 8x minus 36, then what is the length of segment AB? So if M is the midpoint and M bisects the segment AB, that means that AM and MB are equidistant. They are equivalent. So how do we figure out the length of segment AB? So we ultimately want to know how long is this. Well, once we find out that whatever the length of this is, this length will be the same. Okay, so how do we do that? Well, these two are the same, so we can take 5x plus 9 and set it equal to 8x minus 36. So I've just set up an algebraic expression showing the relationship between segment AM and MB. So if I solve this, I prefer to subtract 5x from both sides. And the reason why is because I want my x term to remain positive. They cancel. I have 9 equals 8x minus 5x is 3x minus 36. I will add 36 to both sides. 9 plus 36 is 45. And the 36 cancels, and I have, oops, not 36, but I have 3x. And dividing both sides by 3, I get x equals 15. So if x equals 15, now I can figure out the length of AM. So 5 times 15 plus 9. Well, 5 15ths is 75. 75 plus 9 is 84. So the length of AM is 84. Now, that should also be the same for MB. So what is 8 times 15? So if I substitute 15 for x, I get 8 times 15. And then I need to subtract 36. And I get 84. So both of these segments together, or not together, but both of these segments have a length of 84. Okay, so let's talk about how this would be different. The next example. We have what is the coordinate of the midpoint of this segment? So here we have a segment that's in the XY coordinate plane. Well, the first thing I'm going to do, if possible, is I'm going to identify the ordered pair for the endpoints. And this would be 1, 2, 3, 4, 5, 6, 7. So that ordered pair is 7, comma, oh, I don't know what the end of it is. I don't know why I put that. So that is 7, and then 1, 2, 3. So that's 7, comma, 3. That's the ordered pair 7, 3. This point would be negative 1, 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 8. The midpoint, remember, bisects the segment. So there is a point in here that bisects this segment into 2 equal parts. Okay, so what I want is I want the coordinate of that point. And so that coordinate is going to have an x value and a y value. So how do we find the coordinate of the midpoint? Well, that's where you can find the coordinate of the x coordinate of the point by taking negative 1 for your x value of one point, add to the x value of the other point, and divide by 2. So that's 6 over 2, which turns out to be 3. Then you're going to do the same thing with the y's. You'll take your 8 plus the 3 and divide that by 2. So 8 plus 3 is 11, and 11 over 2 turns out to be like 5.5. So let's see how close we were when we found, or I put that point there. The ordered pair is 3, comma, 11 halves. So 1, 2 over 3, and then up 5.5, 1, 2, 3, 4, 5, and that is halfway between those two. So here is the midpoint, 3, 11 halves. Okay, Sorry, that got crooked. Okay. So, couple more examples. What about this? What is the location of the midpoint located between points P, -4, 4, and Q, 5, 1? So, if I try to figure out what that looks like, I have P, -4, 4, and I have a point at 5, -1. So, over 5, down 1. So, I want the midpoint of this segment. And so the midpoint's going to be somewhere in here. And so I need, sorry about that, I want the ordered pair. And so I will find the ordered pair by taking the x value of one coordinate added to the x value of the other coordinate. So -4 plus 5, divide that by 2. And then take the y coordinates, 1, and add -1 and divide by 2. So this gives me 1 over 2. This gives me 3 over 2. So this point right here, wherever the midpoint is, occurs at 1/2, 3/2. And of course, my drawing is not to scale at all. But that point, 1/2, 3/2, should be over and up. So it's going to be more right there. So that would be 1/2, 3/2. So, yeah, that's right. Okay. And then finally, one last example. Here we want to, the question is, what is the location of endpoint B when endpoint A is located at 2, 4 and the midpoint is located at 6, 3? So if I plot my points and I have a point A at 2, 4, so over 2, up 4, here's 2, here's 4, and I have the midpoint, this is point A, and I have a midpoint that is located at 6, -3. So up 6 and then down 3. This is your M for midpoint. And that point is at 6, -3. I want to know what is the location of endpoint B. Well, if this is one endpoint and that's the midpoint, then B has to be down here somewhere. So, of course, my drawing is pretty bad. So how am I going to do that? Well, I know that I can take my x value of one coordinate, this is x comma y, add it to the x coordinate of the other end point and divide by 2. And I know that the x value of the midpoint is 6. So I have 2 plus x over 2 equals 6. I'm going to do the same thing with the y's. I have 4 plus y over 2 equals -3. If I solve each of these little equations for x and y, I'll have the coordinate of B. Now, I do know that whenever I get my answer, x, the x coordinate of B should be bigger than 6. I also know that the y coordinate of B should be smaller than -3. So let's see what we get. I'm going to multiply both equations by 2, and that gives me 2x, no it doesn't, I'm sorry. I get 2 plus x equals 12, so x equals 10. And then for the y's, I have 4 plus y equals -6 because I multiplied both sides of the equation by 2, and I get y equals -10. So this point, B, has a coordinate of 10, -10.